Hello, differential equation students. In this video, we will simply review derivatives and integrals that are likely to show up at some point in this semester of differential equations. Let's begin with derivatives. Find the indicated derivative. Imagine n and a as constants. We're going to assume that x is the independent variable and that y is the dependent variable. And the reason we can make that assumption is because the derivative notation is dy dx, and dy dx indicates to us that very relationship I just mentioned. We should think of y as the dependent variable and x as the independent. X to the n, we just have the power rule, and power drops down to the front as a coefficient, and the new power is 1 less than it used to be. A to the x. Keep in mind that a is a constant, so this is an exponential function. The derivative of a to the x is itself times the natural log of the base. In particular, the derivative of e to the x, we follow the same general rule as above. It's e to the x times the natural log of e. However, the natural log of e is 1, so typically that's not written or thought about, but it should be thought about. So the derivative of e to the x really just winds up being itself. Natural log of x, the derivative of that is 1 over x. Sine of x, derivative is cosine of x. Derivative of cosine is negative sine of x. Derivative of tangent is secant squared of x. Over to the next column, derivative of cosecant is negative cosecant of x, cotangent of x. Derivative of secant is secant of x times tangent of x. And derivative of cotangent is negative cosecant squared of x. Moving on to the inverse trig functions, we'll just review two of them. The derivative of arctangent of x winds up being 1 over 1 plus x squared. And derivative of arcsine is 1 over the square root of 1 minus x squared. And the hyperbolic. If you may not have been taught hyperbolic trig functions, the hyperbolic sine function, for example, this one here, the hyperbolic sine function, or sometimes we just say sinh of x, is a combination of exponentials. It's e to the x minus e to the negative x all over 2. And the hyperbolic cosine is the same exponentials, but added and divided by 2. And when you differentiate either of these expressions, it turns out that they just toggle back and forth between each other. So the derivative of the hyperbolic sine, or the sinh, is the hyperbolic cosine, or the cosh or cosh of x. And the derivative of cosh of x, or hyperbolic cosine of x, is hyperbolic sine. I won't say more about those other than that. The chain rule. This next table is going to help illustrate the use of the chain rule. Notice we're still trying to find dy dx, so we're treating x as the independent variable. We're going to imagine that n and a are still just constants, but the u is an arbitrary expression. It could be x, it could be a more complicated function, it could be a constant. It really has the freedom to be any kind of expression. So to find the derivative of any expression raised to the n, to a constant, we do what's called a generalized power rule. So the exponent still drops down as a coefficient. The base stays the same. The new power is 1 less. But then we need to multiply by the derivative of u with respect to x. And that's the chain rule part. Multiply by the derivative of the base. From now on, I'm just going to write u primes instead of du dx. But when I write u prime, that u prime is a derivative with respect to x. Just keep that in mind. The derivative of a to the u. It follows the same pattern of a to the x, which is a to itself, or a to the exponent, no change there, times the natural log of the base, and then the chain rule part is now multiplied by the derivative of that exponent. So du dx. E to the u is itself times the derivative of the exponent. In fact, you're going to notice that all the formulas I'm writing in this table are the same formulas that we put up here, except I'm using u instead of x, and there's a u prime being multiplied. It's the presence of the u prime that is the chain rule happening. So the derivative of natural log of u is going to be 1 over u, or 1 over the argument, We call this the argument. Sometimes the input of a function is referred to as the argument. So we do 1 over the argument times the derivative of the argument. And sometimes people will put the derivative of the argument just up top. So it's u prime over u. Derivative of sine of u is cosine of u, but then chain rule. I usually put the u prime in front when I'm doing the trig so that it doesn't look like, if you put it here, some people kind of mistakenly put parentheses around it like that, and that'd be incorrect. It's better or safer just to put it in front. And derivative of cosine of u is negative u prime sine u, and derivative tangent u is u prime secant squared of u. We could do more. I didn't bother doing all of the examples, like I didn't do any of these ones over here with u instead of x, but I trust you to picked up on the pattern here. Right? If these were all u's instead of x's, then there would be u's all over here instead of x's, and then also multiplying by a u prime. Just as a few examples to illustrate this, let's do an example of a u to the n situation. Let's say we had 3x minus 5, and that's being to the 5th, and I wanted to find the derivative of that with respect to x. So the generalized power rule, right, states that the 5 drops down, the base stays the same, the new power is now 1 less, but then we need to multiply by the derivative of the base, which is just going to be 3. And I won't do an example of each of these cases, but let's pick this one here, for example. If I say find the derivative of the natural log of, and I don't know, let's put a sine right there, sine of x. So this is a natural log of u situation, and the derivative of natural log of u is u prime over u. So I do the derivative of the argument, and the argument is sine of x. So we do the derivative of sine of x up top, and then over the argument, over sine of x. And then, of course, we could rewrite that as cotangent of x in this case, etc. I won't do any more examples, but that's the chain rule being used. I take it back. We are going to do the chain rule on the other ones too. We have the derivative of cosecant is negative cosecant cotangent, but then put a u prime in front of that. Negative cosecant of u cotangent of u. Derivative of secant u is u prime secant u tangent u. Derivative of cotangent is negative u prime cosecant squared of u. Arctangent is u prime over 1 plus u squared. Arcsine is u prime over square root of 1 minus u squared. Hyperbolic sine of u is u prime hyperbolic cosine of u. And then the derivative of hyperbolic cosine of u is u prime hyperbolic sine of u. And let's just do one example of one of these. I'm going to pick an arctangent. So if we do the derivative of the arctangent of, let's say, x squared. So the derivative of this will be the derivative of the argument goes in the numerator. So the derivative of derivative of x squared is 2x. And that goes over 1 plus the argument, which is x squared. But then that needs to be squared. So this is effectively the u prime up there over the 1 plus u squared, right, where u is the x squared function. Of course, this can simplify a little bit. We would say 2x over 1 plus x to the 4th. Okay, I'm not going to spend any time doing any other examples. Let's do a quick review of the product rule. If you have a product of u times v, and u and v stand for arbitrary expressions, they could be constants, they could be x, they could be more complicated functions of x, and you want to do the derivative with respect to x, I'll just put a prime there. And the product rule says you do the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. Quotient rule is similar. If you have u divided by v, and you want to do the derivative of a quotient, you do the derivative of the numerator, so u prime times the denominator, minus the numerator times the derivative of the denominator, all over the denominator squared. I like these particular UV rules just because they're maybe a little bit easier to memorize. Notice the pattern that u prime v plus uv prime is effectively the same thing here except subtraction, but then you also need to remember divide by x squared. Let's do just a quick example of just one of these, or maybe one of each. So the derivative of x squared times e to the 3x. So the product rule says do the derivative of x squared, which is 2x, so that's the u prime, times the v, so times the next part, and then plus the first part, which is x squared, the first factor that is, and then I'll times the derivative of e to the 3x. We've got to use a chain rule on the derivative of e to the u, or this is, maybe I shouldn't say u because I'm calling this u. I shouldn't call that u as well. Think of that as e to the w, if you will. And the derivative of e to the w is w prime times e to the w. So the derivative of 3x is 3, and then we just repeat the exponential. And there's some factoring you could do, etc. But let's move on to the quotient rule. Let's do a derivative of, let me give myself a little more space, I'll write it a little bit lower. The derivative of x over natural log of x. Apply the quotient rule. So we do the derivative of the numerator first, which is 1, times the denominator, so just natural log of x by itself, minus the numerator, which is x, times the derivative of the denominator, which is 1 over x, and we put that all over the denominator squared. And of course, this simplifies to just natural log of x minus a 1 all over a natural log of x squared. Be careful not to simplify. You know, some people are tempted to cancel some of these natural logs, but you can't do that because you have subtraction up top. So that's really a good spot to leave our answer right there, applying the quotient rule. One more review about derivatives. Find the local linearization of the given function at the indicated value of x. So this is just a function that, you know, it's whatever. It looks like something. We could graph it if we wanted to. And we're focusing on x equals -1, so x equals -1 is somewhere. And this is not an accurate picture, but just to give you an idea of what we're doing here. The local linearization just really means find the equation of the tangent line. Like if you zoom in at this point on the curve, it starts to look like a line. And that line it starts to look like is the tangent line. So we're really just after the equation of the tangent line of whatever this curve looks like. So we need to get the derivative. And I'm going to rewrite the function using the power. Instead of the radical, I'm going to say 3 minus x raised to the 1/2, and then use the generalized power rule to get f prime of x. So the 1/2 multiplies to the 6, making 3. The base gets rewritten. The new power is -1/2, and then the multiply by the derivative of the base. The derivative of 3 minus x is -1. And now we just want to plug in the x-coordinate in question to get the slope of the tangent line at that location. So the slope of the tangent line will be f prime of -1, which gives us, I'm going to do a little bit of simplifying here, the 3 times the -1, those multiplied be -3. And then the other part is 3 minus x to the -1/2. That's going to be 3 minus -1, because x is -1, and that's going to be under a radical. So we get -3 in the numerator, and we wind up getting square root of 4, which is 2 in the denominator. So there's the slope of our tangent line, -3/2. And now we want the y-coordinate. The y-coordinate is found by plugging in the same x-coordinate, but back into the original function. So it's 6 times radical, it's going to be radical 4. It's going to be a 2 there, times 6 is 12. So there's our y-coordinate. And then we just construct the tangent line by doing y minus y-coordinate is equal to slope, which is -3/2, times x minus x-coordinate. And x minus -1 winds up being x plus 1. Technically, we're done. This is the equation of the tangent line, but sometimes you will see people put this in the form y equals mx plus b. So we get y minus 12 is equal to -3/2 x minus 3/2. First distribute the slope, and now add the 12. So I'm going to add 24/2 to -3/2, and that gives me 21/2. Okay, so there's, you know, any of these, frankly, they're all the same. They're all equations of the tangent line. Now let's do a little bit review of some antiderivatives. To find the antiderivative, we're going to be assuming in these formulas here, in these functions, that the letters are constants unless it's an x. X is the independent variable. So the antiderivative of a constant is a constant times the independent variable, which is, in this case, x, so kx. And then don't forget we need the plus c to give all possible answers. Antiderivative of x to the n. Let me zoom in a little bit here. This is where we add 1 to the exponent and then multiply by the reciprocal of that exponent, plus c. Of course, this only works if n is not -1, because otherwise you can't If you add 1 to negative 1, you get 0, and you can't reciprocate it. So this formula works for every n except negative 1. We should probably make that clear. N can't be negative 1 for this formula. If it is negative 1, then it's really just this case. And when we anti-differentiate x to the minus 1, we get natural log of x. Also, we need to have absolute values on the x because the domain of this x here is x can be positive or negative, but not 0. So I want an antiderivative that has the same domain. And if I did not have the absolute values on that x, then our domain would only be positive numbers, because you can only do logarithms of positive. You can't do log of 0, and you can't do log of negative. But if you have this in absolute value, it turns out that the derivative of this is still this, and we don't have a domain change issue. In both cases, x can't be 0, but x can be any other number. Antiderivative of e to the x is just itself, for the easy case, and add c. Antiderivative of sine is, the derivative of sine is cosine. So some people get derivative and antiderivative of sine mixed up. But if I say this is my answer, cosine of x plus c, and I differentiate to go this way, then there would be a negative here, but there isn't. Right, so we need the negative here. So the antiderivative of sine is negative cosine. Antiderivative of cosine is positive sine, right, because the derivative of sine takes you back to cosine, plus c. It's extremely easy to get these, to get the sign SIGN in the wrong place, because students often early on will get derivatives and antiderivatives of sine and cosine mixed up. Antiderivative of secant squared is just tangent, plus c. Over the other table, you'll notice these are all just the reverses of the derivative table we did earlier. Right, the antiderivative of cosecant squared is cotangent, but we'll need a negative in front of that so that the sign SIGN comes out correct. Antiderivative of secant tangent is secant of x, plus a constant. Antiderivative of cosecant cotangent is negative cosecant of x, plus a constant. Antiderivative of 1 over 1 plus x squared is arctangent of x, plus c. And then we have the arc sine is the next one. And then the antiderivatives of the hyperbolic, they just go back and forth. So these are functions where the derivative of hyperbolic sine is the same thing as the antiderivative of hyperbolic sine. And that's also true for hyperbolic cosine. All right, so there's some basic antiderivatives to know. Then we're going to review some substitution methods to find antiderivatives. An indefinite integral is an integral without limits, if you recall, on the integration sign. And it just means find the family of antiderivatives. Well, the first thing I notice is that the argument of the cosine function is this 4x squared plus 1, and the derivative of that would be 12x. I have a 3x here, but the fact that there's an x here, and the derivative of x squared involves x, it's a multiple of x, tells me that this 3x that's in the front could have been the result of a chain rule, right? I see something of the form u prime times cosine of u, which is what you get after you differentiate a sine of u. So the basic substitution is really reversing the chain rule. We do the step of letting u be equal to the argument, in this case, 4x squared plus 1. We find the derivative of u with respect to x. Notice I'm using full Leibniz notation now, not just u prime, because I'm going to split the differentials up. That gives me 8x dx. From here, there's a few different strategies you can do. Some strategies, oops, I don't need the dx there, not yet, because it's currently written down there. And one strategy is solve this expression for dx and just replace that dx and see what happens. Another strategy is try to take this 3x and this dx together and try to construct that over here and do a substitution on that. It really doesn't matter. I'm going to do the approach where I just solve for dx. So I'm going to take this result right here, cross multiply, so du equals 8x times dx, and then divide both sides by dx. Sorry, by 8x. So we get dx is equal to du divided by 8x. And then I'm just going to substitute that into just this right here and see what happens. Of course, change that to u as well. So we get an integral of the 3x. I'm not focused on that for now. We get cosine of u, and then the dx becomes du over 8x. Now you can see that the x's are going to cancel each other. That x and this x are going to cancel each other. We have a 3 over an 8 as well. That can be factored out to the front of the integral. And we wind up saying, okay, well, what's the antiderivative of just cosine of u du? The du tells you that you can just treat u now as the independent variable as far as doing the antiderivative is concerned. And so the antiderivative cosine of u with respect to u is sine of u. And then here's where the plus c shows up because we just did an antiderivative. And now we do what's called the back substitution, and that is to replace the u once again with what we said it was equal to, which is 4x squared plus 1. So to go back to x's, in other words. And here is our antiderivative. I leave it to you to verify through differentiating and using the chain rule that when you differentiate the thing I just boxed, you're going to get the original problem. This is called the integrand, by the way. The integrand is the function that's inside the definite integral. So we have the integral sign, we have the differential, and the rest of it right there is called the integrand. And when I say integrand, I'm saying this word, integrand. So the derivative of our answer, the derivative of this, should be the integrand. I'll leave it to you to verify that. Let's do the substitution, or the table method, integration by parts. I hesitate to say, I'm going to just show you a way to do integration by parts that does not use u's and dv's. You might have used this formula in a Calculus 2 class, and then you say, hey, I'm going to call part of this u, part of this dv, and then I find u and, or I find v and du, and then I put all the pieces back together and apply this formula. I personally don't like teaching the u's and dv's. I think it gets really cluttered, especially if you have to do integration by parts multiple times. I'm going to teach what's called the table method. It organizes the pieces in the same way as the u's and dv's, but it keeps the pieces organized via a table as opposed to via using letters. So I'm going to make a table with two different columns. One column, I'm going to put a D for differentiation, and the other one I'm going to put an A or an I for integration or anti-differentiation, whichever. I'm going to take the integrand and factor it. Now it's already factored, it's 3x and cosine 4x. And in this case, if I put the 3x in the differentiate column and the cosine of 4x in the anti-differentiate column, and if I do one extra row, meaning I differentiate what's in this column once, that gives me 3, and then I anti-differentiate what's in this column once. Anti-differentiate cosine is sine, but a reverse chain rule means I need a 1/4 in front. Just verify, right? If you differentiate sine of 4x, 1/4 of sine of 4x, you should get cosine of 4x, because the chain rule would output a 4, which would cancel the 1/4. And if I do this is organizing in the following way. This is what used to be u, this is what used to be dv, and what I just found was u prime, or du, and just v. So I'm still doing the u's and dv's, it's just I'm not using the letters to keep track of the pieces. And when you apply the formula, you get u times v, which is this diagonal product. So we do 3x times 1/4 sine 4x. So 3x fourths times sine 4x. And then minus the integral, and then we do v times du. So we do the horizontal product at the bottom of the table, which is 3/4 sine 4x. And then I just got to finish this last integral. And this is me applying the u's and dv formula, but without using u's and dv's. Well, here's the interesting thing. I could do this again. I could let 3/4 be u and sine 4x dx be dv and apply an integration by parts formula again, which is going to be the same thing as me just doing one extra row of this table, right? Because I'm going to leave the 3 in the differentiate column. You're safe to move that 1/4 over here if you want and say 3/4, but you can also just leave it here. It doesn't matter where that constant goes. But if I do one more row, the derivative of 3 is 0, and the antiderivative of 1/4 sine 4x will be divided by another 4, so 1/16, and we'll have a negative cosine of 4x. Let me erase that stuff up there. Now, if you can, let me get rid of that I. We'll just say A for antiderivative. If you can keep this, or do this table in such a way that whatever you started with up in here, and you got to a 0 eventually by differentiating, and you can anti-differentiate this an equal number of times, so that we have, complete rows, then the final result of your anti-differentiation will be diagonal products, which I'll write. Let me use this to keep track. Well, I'm debating what to do here. So you multiply these. I actually like to put an extra column in front here to keep track of the sign because the formula has subtraction involved. So I'm going to put a plus and then a minus and then a plus. And how the table method gets applied is we do this product and we keep the sign. So in other words, we really kind of include that sign as like a positive 1. So multiply all of those. Then you just do these sort of diagonal products, multiply that. And you keep this up until you get to the bottom of the table, and you finish by integrating the final product, which is horizontal. So we have the green and the orange products are diagonal. Those are considered finished, integrated. So the green, when multiplied together, just gives me that first term. Now, when multiply the orange together, we have minus 3 times negative 1/16 cosine 4x. That's going to be just positive 3/16 of cosine 4x. And then we finish by integrating the red. Now, because there's a 0 involved, though, you're really just going to wind up integrating 0. Which is really nice whenever you get a 0 down in your table here, because this will always happen. You just wind up integrating 0 at the end, and the antiderivative of 0 is a constant. So in other words, you just get the plus c that you needed here at the end. Anyway. This is the table method for doing integration by parts. I find it to be a lot cleaner, and sometimes it takes 5 rows to finally get to 0, in which case you do 5 extra rows over here as well. And that's an indication that you had to do integration by parts multiple times to finish the problem. And no one wants to do integration by parts using u's and dv's when you're letting 3 different things be u in your problem. It gets very confusing. Lots of parentheses you need. It's just a big headache. This table method with these alternating signs here in the front, which accounts for the nested subtractions that would happen if you did integration by parts formulas multiple times, really makes just a clean, fast way to do integration by parts. Let's do just another one to show you the advantage of this. So we have a differentiate column and an integrate column. Let me make that look a little bit better. Or an anti-differentiate column. Again, I'm going to put the polynomial and then the trig. I'm going to put the polynomial in the differentiate column because it will differentiate to 0. I'll put the trig in the anti-differentiate column and differentiate the left column until you get to 0. So 6x, then 6, then 0. Anti-differentiate this column an equal number of times. So there's the first antiderivative. The next one will be negative 1/16 cosine of 4x. And then the last one will be negative 1/64 sine of 4x. If you're not sure you're getting these signs here correct as you're doing this, just remember derivative of negative sine will be negative cosine, good. Derivative of negative cosine will be positive sine, good. Derivative of positive sine will be positive cosine. So looks like I'm doing the antiderivatives correctly. Now we have to do then I do the extra column over here with the pluses and minuses. The plus, minus, plus, minus. Always start with plus. And now we do our alignments. So we do this product, then we do this product, and we do another diagonal product, and then we finish with a horizontal product. So the orange product is going to be positive 3/4 x squared sine 4x. The green product will be 6x over 16. That's going to be 3x over 8 and positive. So positive 3x over 8 of cosine 4x. Then I do the blue product. It will be 6 over 64. That's going to be 3 over 32 and negative. So negative 3/32. And then we have that sine 4x. And then we do the red product at the end and integrate it. You always integrate the horizontal product. You end the table with an integral. However, we're going to be integrating 0 again, so I could just say plus c. And we're done. Just like that, we get this antiderivative. This would have been 2 nested integration by parts here. with u's and dv's, and this is just much better. In this case here, again, integration by parts. You might start to think, okay, I'm always going to put a polynomial in the differentiate column because polynomials will differentiate to 0. Oops. That should be a. So it's tempting to put the x cubed here and the natural log of x here. The only problem is that the antiderivative of natural log of x, either you don't know it or it gets it. The antiderivative is this. It's x natural log of x minus x. It gets more and more complicated. Turns out that this problem is a lot easier to switch these around, put the natural log over here and put the x cubed over here, and do one extra row and then stop the table. You also don't have to keep going until you get to 0, because if you keep differentiating this, you will never get to 0. It'll just get worse and worse. So it's not always the case that you want to do this until you get to 0 in the left column. Just do that one extra row. So we get 1 over x is the derivative of natural log of x. Do one antiderivative of x cubed. That's 1/4 x to the 4th. And then stop the table. Of course, put your sine column over here, plus minus. And we're going to do this diagonal product is done. And then we have a horizontal product to finish this out that we need to integrate still. So the orange product is positive. It's going to be 1/4. I'll put the x to the 4th first and then the natural log of x. And then the red product is going to be negative and it needs to be integrated. It's going to be 1 over x times 1/4 x to the 4th dx. So then simplify this and then see if you can integrate it to complete the problem. All right, so the first part I'm just rewriting. Then we have minus, I'll pull the 1/4 out to the front. The integral in x to the 4 over x is just x cubed. And question is, can I integrate this and finish it? The answer is yes, so we just keep going. If the answer is no, then maybe you can come back over here and rethink how you split this up. But, oops, for the 4 there. And antiderivative of x cubed is a 1/4 x to the 4th, so we have a 1/16 now, x to the 4th plus c, and we are done. All right, here's a variety of different exponentials. I'm not going to finish out these problems, but notice how similar they all kind of look, and they just require different techniques. If I saw this x squared over times e to the x, I'm going to do integration by parts, and I'll use the table method to do it. I'll just get it started and let you finish on your own. But I'd put the x squared here and the e to the x here, because I can differentiate this to 0, and I can anti-differentiate this equally the same number of times and do it easily. So that's the approach I would take there, integration by parts. This next one, the x squared is up on the exponent now, and I notice that the derivative of x squared involves an x. So this looks a lot like the result of a chain rule happened, which tells me I should do a substitution on that x squared. So classic U substitution will help us finish this problem. I will leave it to you to finish. And this last one here, it turns out that this one has no known antiderivative. At least no known antiderivative in closed form. Sometimes our methods are not able to produce a function that is the antiderivative of another function. At least a function in closed form, I should say. And notice how with just these all look pretty similar on the surface, but just a few subtle changes dramatically changes whether we can anti-differentiate in the first place, and then what strategy we would use to get the antiderivative in the second place. Okay, here's a few more antiderivatives to learn. If I'm doing the antiderivative of natural log of x, the strategy here is to do, so if I were to say, hey, what's the antiderivative of this? I would do the dA column, I do integration by parts. I'll put the natural log of x here, and there's nothing left. Well, you can put a 1 in the anti-differentiate column, and do one extra row. So the derivative of natural log of x is 1 over x, and the antiderivative of 1 is x. Put your plus minus over here, and then do the diagonal product first. So we get x natural log of x minus, and then the minus comes from that minus there, and then multiply these, but integrate that part still. So minus the integral of 1 over x times x. And of course, 1 over x times x is 1, and then the antiderivative of 1 is back to x. So we get that the antiderivative of natural log of x is this expression. I wrote that earlier, but this is how we get it, using integration by parts. For tangent of x, me go ahead and just get rid of that stuff. For tangent of x, you want to think of it as sine over cosine. Right? Think of sine of x, tangent sine of x over cosine of x, and then you let u be the denominator. So the derivative of that will be negative sine of x dx. Therefore, my original problem, which was the integral of sine of x over cosine of x, we're going to call this down here u, and notice that if I move this negative right here, move it to that side over there, then I would have sine of x times dx is equal to negative du. So there's a sine of x times dx. That becomes negative du. So this really just winds up being really negative 1 over u du, which is negative natural log of u. And then we do the back substitution. Let me move that up here actually and put my answer right here. So we get negative natural log absolute, and u is cosine of x. Now you might remember your log properties. This negative can be brought up as a power. And so you could say, you can say the natural log of cosine of x raised to the minus 1, and the reciprocal of cosine is secant. So sometimes you will see an answer here that is just natural log of secant of x. Either one of these antiderivatives is fine for tangent. For cotangent, you do something similar. I'm not going to do all the details, but you wind up getting the natural log of sine of x. The antiderivative of secant and cosecant, these are just, they need to be effectively just memorized. The antiderivative of secant is the natural log of the secant of x plus the tangent of x, and then plus c. I leave it to you to verify that through differentiation that the derivative of what I just circled will be equal to secant of x. And the antiderivative of cosecant, there's really one of two acceptable answers. You can do natural log of cosecant of x minus cotangent of x, or you can do the negative of the natural log of cosecant of x plus cotangent of x. I see both of these, and they're both acceptable. I leave it to you to verify that both of them do produce cosecant of x when you differentiate. All right, some trig identities that are going to be useful when you have to integrate trig expressions. You should have the Pythagorean identity for trig, both versions of it, memorized and ready to use. And these other ones here, I usually just recommend you just memorize these identities. They are helpful in doing integrals involving trig and doing back substitutions. Let's just go ahead and see how they might be useful. So integrating, some strategies for integrating powers of sine. Whatever I do here is going to be pretty similar for how you would do powers of cosine. Integral of sine squared. I'm going to use this, I call this the power reducing identity because it goes from sine squared to just cosine, no power on it, but it doubles the angle. Notice that the angle here is theta and the angle over here is twice that. That's all you have to remember, is that the angle doubles, but the power goes away. So if I use that over here, we get 1/2 the integral of 1 minus cosine of 2x dx. And then from here, it's rather simple to get an antiderivative. You get x for the antiderivative. Antiderivative of cosine 2x is negative 1/2 sine 2x. And here's an antiderivative. This is good enough, although you could use the sine 2x and go back to just x. And so another way you'll see this is 1/2 x minus, so this sine 2x is equal to 2 sine x cosine of x. And then the 2 I just mentioned is going to cancel with that 1/2. So we really just get sine x cosine x. So here's another version of the answer for this one. To do sine cubed, I didn't really give myself a ton of space here. The strategy will be to split off a sine, something like this. And I won't finish this problem, I just want to show you the basic strategy. And then this sine squared, we're going to use the Pythagorean identity to help us with that. So you can rewrite that as 1 minus cosine squared. And then a u substitution on cosine will help get us out of the woods. Because the du will take care of that sine x dx. This is called saving a sine and then letting u be cosine. If you have sine to the 4th, you're going to want to write that as sine squared squared and then do the power reducing identity twice. So you wind up getting 1/4 of 1 minus cosine 2x, and that's multiplied with itself, so I'll just put a square there. And then you're going to want to FOIL that next. So you have 1/4 integral. When you FOIL this, you get minus 2 cosine 2x plus cosine squared of 2x. And that should be a 2x, not x. I really didn't give myself a lot of space here. And then this is cosine 2x, not cosine squared. So that we can integrate that and we can integrate that. But this one here, to integrate, we're going to have to do a power reducing identity again. So we wind up getting 1/4 times the integral 1 minus 2 cosine 2x. And the power reducing identity on this will produce a 1/2 times 1 plus cosine, and then double the angle again to 4x. But the power is gone. Then you could distribute this 1/2, and then you can integrate all the terms separately. I'll leave it to you to finish this problem. But that's what you have to do when you have like a sine to the 4th. If you had sine to the 6th, it'd be something similar, but just a lot of power reducing identities. And sine to the 5th. Here we're going to save a sign. So we have, and break up, and the other sine to the 4th, we're going to convert to sine squared squared. So you have sine squared squared times the 5th sine is right there. And this sine squared we're going to convert to cosines, not using power reducing, but using Pythagorean. So we have 1 minus cosine squared of x, that's being squared, times sine of x dx. And now if you just let u be cosine, you'll be able to finish out this problem. So just quickly at a glance, when you have an even power of sine, you just do power reducing identities. And sometimes you have to do it multiple times. When you have an odd power on sine, you can save a sign, convert the other signs to cosine using Pythagorean identity, and then do a substitution on cosine. The strategies are very similar for when you're doing, if these are all cosines here instead of sines to begin with. Trig substitution strategies, integral of the square root of 16 minus x squared. We're going to use a substitution that will allow me to use a Pythagorean identity of trig. For example, I see a constant minus x squared. This is a case where if I let x be equal to the square root of this constant, which is 4, times the sine of a new variable, so I'll say sine u, that this is going to allow, this substitution will allow this expression here to simplify by using the Pythagorean identity. However, I have to replace the dx too. So we got to find the derivative of x with respect to u, which is 4 cosine of u du. Let's make these changes. Change this x to 4 sine of u and then square it. So that's going to be 16 sine squared. So we have a 16 minus a 16 sine squared of u. That's all in a square root. And then the dx becomes a 4 cosine of u du. Now the nice thing about this is 16 can be factored out now. Those coefficients match. Be factored out, and you're left with a 1 minus sine squared. Right, so the 16 factors out, leaving a 1 minus sine squared. That's all inside a square root still. The rest of this copies down. So times 4 cosine of u du in an integral. And 1 minus sine squared is cosine squared. So Pythagorean identity gets used. And then you can square root the two pieces separately. So you really just get 4 cosine u right there. Times another 4 cosine u. So this winds up being 16 integral of cosine squared of u, and then I would do a power reducing identity, which we just talked about. So I won't finish this because it's looking a lot like how you would do this approach. When you have a sum of squares, I'm going to wind up leveraging this identity because I see a sum of squares here. So I want a constant plus a variable squared. I want that variable to take the form tangent so that we can condense that to a secant squared. So I want the x in this case to be a 4 tangent of u. Dx will therefore be 4 secant squared of u du. We've got to also replace the dx. And when you plug everything in, you wind up getting an integral of the square root of 16 plus 16 tangent squared. Square root that. And then we have the dx is 4 secant squared of u. factor out the 16, you're left with a 1 plus tangent squared, which is the same thing as secant squared, and then you can square root the 16 and the secant squared, and you wind up getting an integral of 4 secant u times 4 secant squared u. This sets us up for an integral of secant cubed, which is actually a complicated integral to do. This will be 16 secant squared, or secant cubed of u. To integrate secant cubed of u requires several techniques to get an answer out of this. I'm not going to review those techniques now. Feel free to look it up. I do have the antiderivative secant cubed memorized. It's the average of the derivative and antiderivative of secant. So in other words, the derivative of secant is secant tangent. The antiderivative is antiderivative secant is natural log secant u plus tangent u. And then you average them. So you add them together and divide by 2. So you could put that in parentheses and put a divided by 2 out there. And I'm going to stop this one here. And then when we have a difference of squares again, but this time the difference, compare it to this difference of squares, this time it's variable squared minus constant. This is a case where you want to leverage the tangent secant Pythagorean version, but we want x to be 4 secant of u. Because looking at Pythagorean identity right here, if I subtract the 1 over there, then secant squared minus 1 can be condensed to tangent squared. So I'm going to use a secant here as a way to simplify this integrand. Dx will be 4 secant u tangent u. And I'm going to not continue this one. I just want, just to get it started, to show that there's 3 situations in which you would want to do a trig substitution. Difference of squares of one type, difference of squares of the other type, and then a sum of squares. These are your cases. And you're going to use sines in one case, tangents in another case, and secants in the third case. Also, just remember how to do the back substitutions. When you do get a final answer in terms of u, and notice that I left off a u here in my answer there, I just caught that. When you do get a final answer in terms of u, you want to be able to do the back substitution, and the easiest way to do that is to take this statement here, solve it for sine u, so this would read sine of u is equal to x over 4, and then make a reference triangle, where the angle is u, and the sine is x over 4. Well, sine is opposite over hypotenuse. So this statement right here suggests this reference triangle. The sine of u is opposite over hypotenuse. And then you can use Pythagorean theorem to get this side as the square root of the hypotenuse squared, which is 16 minus the other leg squared. And now you have a reference triangle to convert. Let's say your answer involves, let's say you had to do a tangent of u in your answer. Well, then you would just look at this reference triangle, do tangent by doing opposite over adjacent. So you create that reference triangle to help you to do the back substitutions for these kinds of substitutions. Okay, I'm looking at the slides left. We only have 3 more, and this will be an extensive review of integration techniques. Integration by partial fraction decomposition. This will certainly surface in this class. When you have a rational function, so a polynomial over a polynomial, like we do here, try to factor the denominator and see what happens. If we can factor it, then we can try to decompose this. So the denominator factors to x plus 2 times x minus 1. So it does factor. So we're going to try to decompose this expression into, we're going to split the denominators up. And then we have to determine what unknown numerators are needed in order to make the 2 expressions here the same. And the general rule for decomposing, if you have 2 factors here, then you should have 2 fractions over here. And if your denominator is a linear factor, then your top should be an unknown constant, which is degree 0. So this is degree 1, and this is degree 0. Degree 1, degree 0. So we put these unknown constants up above, and we just now have to determine what a and b are so that these 2 expressions are in fact equal. Well, the way to do this is to next multiply both sides by the denominator, by the common denominator, if you will, the x plus 2 times x minus 1. Distribute this to all 3 terms and simplify. So you wind up getting just x plus 8 all by itself equals a times x minus 1, because the x plus 2's cancel for that fraction, and the other fraction is the x minus 1's that cancel. So we have b times x plus 2. And then from here there's a variety of strategies. One is to make a choice of x, like that will cancel an unknown, like let x be 1. And watch what this does. This is nice. Plug in a 1 for x, you get a 9 on the left side, and plug in a 1 for x on the other side, you get a 3b, because the a's will cancel when you plug in 1. This helps us find out that b has to be 3. Now to find a, I should let x be -2, because -2 will cancel the b but leave the a. But I'm going to show you just a different strategy. Another way is to distribute everything on the right side of the statement. So you have x plus 8 is equal to ax minus a plus bx plus 2b. Then group by similarity. So we have the x terms there. We can group those together. So we have x plus 8 is equal to a, and then factor out the x. So a plus b times x. And then the constants are, there's a positive 2b and a negative a. Now, the coefficient in front of the x on the left side of this equation is an implied 1. Right? So the coefficient there has to match the coefficient of the x on this side. And the constant on this side, which is 8, wrong marker, has to match the constant on this side, which is 2b minus a. So this allows you to create a system of equations that says a plus b have to be equal to 1, and 2b minus a has to be equal to 8. Then you can solve this system. If you add the two equations together, you get 3b has to be equal to 9. And notice that gets us to the b equals 3 right away as well. And then plug in that b equals 3 into either of these equations and solve for a, and you're going to get a is going to be -2. All right, this is exactly what you would have had if you had just gone up here and plugged in -2 for x. Sorry, if you'd plugged in, yeah, -2 for x. All right, if you plugged in -2 for x, this would have gone away. This would have been -3a, and this would have been 6. So you'd have 6 equals -3a, therefore a is also -2. Okay, anyway, let me move this around a little bit and finish up the actual problem. We haven't integrated yet. So we can rewrite the original problem instead decomposed. Put a over x plus 2, so a is -2, that goes over x plus 2, plus b, which is 3, over the other factor, which was x minus 1. So we do this decomposition. Now I can integrate term by term. So we get a -2 times the natural log of x plus 2, and then plus a 3 times the natural log of x minus 1, and we are done, plus c. So do a decomposition. Here's another decomposition. I'm going to go ahead and factor that denominator. So we have 3x plus 1 all over. I can factor out an x that leaves an x squared plus 1. And x squared plus 1 is prime. It's a sum of squares. However, I do notice that there are two factors. So I'm going to have two fractions in my decomposition to split the factors up. Above the x goes an unknown constant, so I'll put an a, because 1 degree less. But above the prime quadratic, we have x squared plus 1 that does not factor more. Above it goes an unknown linear expression, first degree, so we have to put a bx plus c up here. And just for pointing out, if you had a denominator that was something like x times x minus 1 cubed, then really there's 4 factors here. So you would do 4 denominators, and then you would put your unknown constants, because each denominator is linear, so unknown constants. But then there's a rule for doing decompositions that when you have a repeated denominator, you also need to keep increasing the power on that repetition. So this would be the final setup for your decomposition in a case like that. Just mentioning that briefly. To finish out this one here, if we multiply both sides by the common denominator, we're going to get 3x plus 1 is equal to a times x squared plus 1 plus, and then bx plus c times an x. I'm going to do the approach where you distribute everything on the right side and group similar terms. So we have 3x plus 1 is equal to ax squared plus a plus bx squared plus cx. Grouping the terms together, we have a plus b all times an x squared. We have just a cx, and we have an a. Right, so there's the x squareds, the x's, and the constants. Now the other side of the equation has no x squared, so you could force it. You could say 0x squared, just to recognize that coefficient should be 0, plus 3x plus 1. And then when you group terms together, the 0 has to be equal to a plus b. The 3 has to be equal to c. And the 1 here has to be equal to that a. So we get all of them pretty quick here. A has to be 1. C has to be 3. And since a plus b has to be 0, and since a is 1, I know that tells me that b has to be negative 1. And then I can rewrite the problem. We have a over x, so we have 1 over x. We still need to integrate. Plus bx, so negative x, plus c, so plus 3, all over x squared plus 1. And then we get this far. Now from here, I recommend splitting this x squared plus 1 under each part of that numerator. So we get integral of 1 over x minus x over x squared plus 1, and then plus 3 over x squared plus 1. Now this part here will give us natural log of x. This part here will give us 3 times arctangent of x plus c. And to finish this one, I won't finish it. You're going to have to let u be that denominator, because the derivative of x squared plus 1 is equal to 2x, and it's a multiple of x, so that'll help us finish that problem using a basic substitution. Okay, and finally the last slide. Find the function y that meets the given condition. So we know the derivative and we know y of 0 is 3. So we just have to go from y to find y. I just have to do the integral of y prime, the indefinite integral. So y is equal to, we get 2x squared minus or plus cosine of x plus c. So this is the answer. That's the family of functions. We want to find the specific function that also satisfies this condition. So we know that when you plug 0 in for x, you should get 3 back for y. So 3 for y and 0 in for x. That gives me 3 is equal to 2 times, that's 0, plus cosine of 0, that's 1. And then, so c is going to be 2. So the specific function we're looking for is 2x squared plus cosine of x plus 2. This is the function whose derivative is 4x minus sine x, and that passes through the point 0, 3. And that wraps up our review.